As we've seen in previous videos, differential amplifiers are pretty useful circuits. In particular, the op-amp can be used to design a number of very interesting circuits that can do a number of useful things. But what's inside of an op-amp? If you start with transistors, how can you arrange these transistors so that you get a good differential amplifier? That's what we're going to talk about in this video, how to design a differential amplifier. Now, we're not going to be designing an op-amp, but we're going to design a basic differential amplifier that can accomplish most of the tasks that an op-amp can accomplish. To start off with, let's design what characteristics a good differential amplifier could have. An ideal differential amplifier has two inputs, one voltage V1 at the non-inverting pin and another voltage that we'll call V2 at the inverting pin. Ideally, a differential amplifier subtracts these two signals, and then at the output, it just gives us some large gain, A sub D times the difference. Ideally, this amplifier will have infinite input impedance. That means that it won't be using up any current from either of the two input sources. It should have infinite gain for the differential signal. That is, A sub D should be a very large number. It should have zero common mode gain. That means that if V1 and V2 both increase by some very small amount, that won't show up at the output. And if it would, then the formula that I have written down wouldn't be correct anyway. It should also have zero output impedance, which means that the output of the amplifier should behave like a perfect voltage source. There should be no voltage divider internal to the amplifier. Finally, it should have a very large bandwidth, and ideally infinite bandwidth, meaning that no matter what frequency I feed into this amplifier, the response of the amplifier should be the same. This is an example of a differential amplifier, and this is the circuit that we're going to be analyzing firstly. It's not a perfect amplifier, but again, it accomplishes most of the tasks that we want a differential amplifier to have. We're going to be analyzing the circuit, but first take note of where the inputs are. We have one signal that we're going to be feeding into the base of transistor 1 here on the left, and we have another input that we're going to be putting on the base here of transistor 2 on the right. The transistors are both biased in the forward active mode, so we're going to have some large positive VCC power supply here at the top, and then we're going to be having some lower negative VEE power supply down here at the bottom of the diagram. Let's start off by assuming that all of the DC voltages here are okay, and I'm just going to do an AC analysis. My goal here is to find out how the output voltages that I have labeled here, Vout1 and Vout2, depend on the input voltages Vin1 and Vin2. Now, since we have two input voltages, I want to handle them one after the other, so I'm going to be using superposition to find the output voltages. In other words, I'm first going to find the output voltage due to source 1, then I'm going to find the output voltage due to source 2, and then I'm going to just add them together. First, let's find Vout1 and Vout2 due to Vin1. In order to do that, I'm going to have to zero out the second source, so I'm going to ground Vin2 temporarily. For simplicity, I'm going to be assuming that we don't have any source impedance, and I'm going to assume that we don't have any load attached to the circuit. So I'm basically assuming that Vn1 is a perfect AC source, and I'm neglecting any DC offsets here for now. Let's first find Vout2, and then after that we'll find Vout1. I'm going to go ahead and label the emitter resistances little r sub e in both of these transistors. Furthermore, because of the symmetry of the situation here, I'm going to assume that those two r sub e's are exactly the same. I can do that because both of these transistors basically have the same emitter resistor, the same collector resistor, and the same voltages around them. The signal that starts over here at the base passes through the first transistor, and then it passes through the second transistor. So we kind of have two amplifiers here. What kind of amplifiers do we have? Well, the signal starts here at the base and winds up at the emitter. That's common collector amplifier, isn't it? Then the signal starts at the emitter and it passes through the transistor and winds up at the collector. That's a common base amplifier. Let's draw an equivalent circuit model for the common collector and common base amplifiers that we have. First, we have our source Vn1. Then we have a resistance R sub E. The signal then finds resistance big R sub E, and then we have a path also to ground from the second transistor. That's the common collector portion. Now for the common base portion of our signal, we need to find out what the voltage gain is. And as you might recall if you've watched my video on common base amplifiers, the gain of a common base amplifier is given by this resistance looking up from the collector divided by this resistance looking up the emitter. So we have R sub C divided by little r sub E for this voltage source. We don't have any output voltage divider here because Vout2 appears without a load. So we can just write Vout2 there. And that was for the common base part of the signal. So we now have an equivalent circuit diagram which I can use to find a formula for the gain. From the first circuit, we have a simple voltage divider. Then from the second circuit, we have only a source. The first fraction involves two resistors, a really large one and a really small one, so we can pretty much neglect the large one. That would give us RE divided by 2RE, or simply 1/2. This means that Vout2, due to source Vn1, is approximately RC over 2RE. Now that we found Vout2, let's go ahead and find Vout1, and again that's going to be due to source Vn1 only. Let's redraw our circuit just a little bit to make this clear. We have a DC power supply, a large resistor R sub C, then our output voltage Vout1. Finally we have our first transistor with input Vn1. Then we have an emitter resistor. We also have a second effective emitter resistor that leads to ground through the base of transistor 2. I'm treating both DC power supplies as AC grounds, so I could have just marked minus VEE with the ground here as well. This transistor has an emitter resistor that's given by little r sub E, and I notice that the signal enters the base and exits at the collector, which means that for the purposes of finding Vout1, this is just a common emitter amplifier. The gain of a common emitter amplifier is the resistances at the collector divided by the resistances at the emitter. And we don't have any input or output voltage dividers here, so I'm not going to bother to draw the small signal equivalent circuit. We can just go ahead and write the answer by inspection. Output 1 due to input 1 is just minus RC divided by all these resistances down here, which is RE plus big R sub E in parallel with little r sub E. If we then make the same simplification over here that we just made and assume that RE is large enough that it can be neglected, then these two resistors in parallel are pretty much just RE. We then conclude that output 1 due to input 1 is just minus big R sub C divided by 2 little r sub E. You might notice that's just the negative of what we found before when we were looking at Vout2. In both formulas for the gain, it's also a little bit interesting that big R sub E doesn't appear in the equation, and that's actually a really good thing when it comes to integrated circuit design. If we want to increase the gain with a traditional common emitter amplifier, for example, we might need to have a large coupling capacitor to bypass that emitter. Here, though, you have a very large gain without the need of a capacitor. And capacitors, especially large ones, are difficult to build on integrated circuits. So here we have a large gain, given that little r sub E tends to be a very small number without the need of a bypass capacitor. So that's one of the advantages of this particular circuit that we can already see from these two formulas for the gain. We've already found the two output voltages due to source 1. Let's now find the two output voltages due to source 2. If I look back at my circuit, I see that previously my strategy was to zero out input 2 and apply my signal to input 1. So now I have to do the opposite. I'm going to have to zero input 1 and apply my signal to input 2. Or effectively, we already have the answers. I just need to relabel them. In other words, because the circuit is symmetric, I can just swap these two numbers and I should still get the same answer. Likewise, with this equation up here, I can just swap these two labels and the answer should be the same. We have 4 different equations for the gain. On the next view graph, let's collect these into a single box. We're trying to create a differential amplifier, so let's take a break and summarize what our goal here is in all of these derivations. If I eventually apply a differential signal V sub D across these two terminals, then what I want is the output, either V out 1 or V out 2, to give me some gain times this V sub D. Let's see if that's where we're headed. We can already see from what I've drawn that V sub D can be defined as the difference of these two voltages. We could also consider splitting V sub D in half in order to give us a more convenient ground for our circuit. So let's go ahead and do that. In other words, I can just define Vn1 as half of my differential voltage, and I can define Vn2 as the other half of my differential voltage. You can see that if I subtract these two signals from one another, the equation gives the correct result. Everything's okay. We have 2 outputs here, V out 1 and V out 2. For now, I'm just going to concentrate on V out 2. Let's start with this equation right here and rewrite it in terms of V in 1 so that it's a proper voltage gain. We can then subtract in our new definition for V in 1 in terms of the differential signal. Let's now do something similar for the second equation for V out 2. We're going to write it as a proper gain, and we'll be substituting in our second input voltage in terms of our new definition. It's minus V sub D over 2, and those minus signs are going to cancel. Let's go back and specify that this was V out due to the first source, and this is V out due to the second source, using the principle of superposition that I said I was going to use when I started this whole derivation. We just need to add these two signals together to find the total V out 2 due to both inputs. So due to source 1, we have RC over 4RE, and due to source 2, we have the same thing. These just add. So let's now write this as a gain. We'll draw a box around it because we've basically just found the AC differential gain of this circuit. Sometimes this is called the single-ended gain because we're only taking the output at V out 2 and we're kind of not worrying about V out 1, or we're not connecting it up to anything. What do we notice about this formula? Well, the first thing I notice is that the gain is probably going to be good and high because we can choose a large collector resistor R sub C, and we know that intrinsically little r sub b is probably going to be a small number. We don't need any bypass capacitor in order to give us this high gain. On the other hand, if we want a very large gain, we would want to use a very large R sub C, but if we use a collector resistor that's a bit too large, we could wind up saturating our transistors, and we wouldn't want that to happen. Everything here is contingent upon those transistors operating in the forward active mode. We've found the differential gain, but what about the common mode gain? How is this circuit going to behave if both inputs Vn1 and Vn2 have some signal common to both? First of all, let's do a little bit of a review to remind ourselves what common mode gain and differential gain actually mean. Let's let V1 have some common mode component and some differential mode component. If the common mode signal is 0, we wind up with the equations we just used. Let's let source 2 also have some common mode component and some differential component. If V sub Cm equals 0, then we wind up with the same equations that we just used. You could think of these two equations as a simple mathematical transformation. We started with voltages V1 and V2, and we redefined them in terms of VCm and VD. Another way to think of these two equations is a transformation between the two sources on the left and the three sources on the right. You'll notice that if we add these two signals together, then V1 plus V2 is just 2 times the common mode voltage. I could then write the common mode voltage in terms of V1 and V2. It's just the average. If I subtract these two voltages from one another, V1 minus V2, then I just wind up with the differential voltage, which is exactly what I expect here. Let's summarize these two equations because we're going to be using them now to find the common mode gain of the same circuit that we've just found the AC differential gain for. So we have the same circuit here that we had before, but I'm now going to include all of the DC offsets into the analysis. So this is going to be a little bit more complete than the Reef analysis that we've just taken. Let's label some of these currents. I'm going to call this IC1. Let's call this IC2. We again have little r sub e for both of these transistors. Let's call this IE1, IE2. Let's call the voltage here VE, and both emitters are attached together with a wire, so we only have one emitter voltage. Let's apply the Kirchhoff voltage law in order to find V sub E by looking at the left half of this circuit. So V sub E is going to be a lower voltage than our input voltage V1. There's going to be a voltage drop, so let's go ahead and write that voltage drop. First of all, we have some voltage drop due to that internal R sub E for the transistor, but we also have a 0.7 volt drop due to the internal diode because I'm now considering the DC analysis as well. We could perform this same Kirchhoff voltage law for the transistor on the right, and I can then get a similar equation, Vn2, and now we're dropping across this little R sub E on the right, so it's going to be IE2 this time. We can then apply the Kirchhoff current law at node V sub E. If I sum up these two currents coming into that node, I get IE1 and IE2. And the current out of the node is just given by Ohm's law across resistor R sub E. Let's first concentrate on these two equations, and I'm going to add them together. If I add these two equations, on the left side, we're just going to have 2VE. Then on the right side, we're going to have Vn1 plus Vn2. Then for the second term, we can factor out an R sub E, and then we have 1.4. We can identify this as just 2 times our common mode voltage, and then for these two currents, I can substitute in for our third equation down here. Let's rewrite it. Let's split this term here on the right and move part of it over to the left. So the first half of it, I'm going to split it off and write it on the left side here. The right half, I'm going to leave it alone. Let's now factor out V sub E. For this term in brackets, I want to multiply the 2 times RE so we can make proper fraction. Let's now move what I have here in parentheses over to the right-hand part of the equation. So it winds up inverted and then next to the 2 in front of VCM. I don't really want to write the rest of it. I just want to note that everything in the blue brackets there is a constant. When I say a constant, I mean that it doesn't change when I change either Vn1 or Vn2. So it's not dependent on the input. It's just a constant. So when I take this constant and I divide it by those other resistances, I'm going to get another constant. I don't really want to keep track of it, so I'm just going to write constant over there. Now I want to turn my attention back to these two equations that we started with, and instead of adding them, I'm going to subtract them. If I take VE minus VE, I get 0. I then have Vn1 minus Vn2. Then I have the first minus the second, so we wind up with a plus sign here. And the 0.7s go away. This is just my differential voltage that I've just defined. I now want to move the differential voltage to the left of the equal sign, and I'm going to also move the emitter resistance to the denominator. I'm now going to rewrite this equation that we started off with just next to this one. Let's add these two equations together. I can now solve this equation for IE2. Now I'm going to find Vout2 by applying the Kirchhoff voltage law across resistor RC. Vout2 is just my power supply voltage minus the voltage drop across that resistor. We can write IC2 in terms of IE2, but they're almost the same. The difference is a factor of beta over beta plus 1. Let's rewrite this. And now when I've reached IE2, I'm going to substitute in for what I've just found right above. Let's go ahead and rewrite Vout2, but I'm going to take note that VCC is just a constant, and VEE over RE is also a constant. Ignoring those constants momentarily, we have beta over beta plus 1. Let's pull the RC inside, and we have VE over RE. And then we have a bunch of constants, and they're constants because they're either fixed components in the circuit like resistors, or the power supply voltages, or some combinations of them. There's no dependence there on either of the two input voltages. What I now want to do is take my previous equation for V sub E and substitute it into this equation. Let's write the RE first, and now I want to write my equation for V sub E from above. We're going to have some constants as well, but let's group them with the ones that we've already written over here. We have some cancellation here, 2RE. Let's write this one more time to clean everything up. So from the equation that we've just found, we can draw some important conclusions. The output voltage, Vout2, is a linear combination of the common mode voltage and the differential voltage. This term is therefore the common mode gain. This term is therefore the differential gain. What we can see is that neither expression for the common mode gain nor the differential gain contain the power supply voltages. So we can do whatever we want with VCC and VEE, and it's not going to affect the common mode gain or the differential gain. All it's going to do is introduce an offset into our output voltage. It might shift Vout2 up or down, but that doesn't matter when we're thinking about common mode or differential gain. Secondly, what I'd like you to notice is that the expression for the common mode gain is not 0. Ideally, a differential amplifier would have a 0 common mode gain. We can make the common mode gain here better if we use a large emitter resistor R sub E. That lowers down ACM. Nonetheless, whatever we do, this is not an ideal amplifier because the common mode gain is obviously not 0. Let's move on to an example and see what typical values of common mode and differential gain might be for this particular amplifier. Let's give it some reasonable resistors, 5 kilo ohm, 9 kilo ohm down here at the emitter, and differential power supplies of 10 volts. Here's the expression that we just derived. Let's assume that the betas of our transistors are reasonably high, so I can approximate this fraction as 1. I'm now going to have to find little r sub e, so I need to do some sort of DC analysis to our circuit over here. Let's assume that our input voltage has no DC offset, so I'm going to assume here that there's 0 volts DC, or equivalently that VN1 might be a purely AC signal. This means that our DC voltage here would be minus 0.7 volts. We now have enough information to find the current through this resistor using Ohm's law. So we have 9.3 volts across the resistor if I subtract these two voltages, and we have 9 kilo ohm resistance there. So this gives us a current of about 1.03 milliamps. From a DC standpoint, I can assume that things are well balanced. So let's just estimate our emitter current over here as being approximately half of I. It's probably a reasonable assumption here for finding little r sub e in any case. So we wind up with 0.52 milliamps. If we're at room temperature, then r sub e is going to be 26 divided by the 0.52 that we just calculated, giving us 50 ohms. Here's our common mode gain, and we can go ahead and substitute everything in. So RC is 5K, RE is 9K, and we just calculated 50 ohms. So this works out to be minus 0.28. Ideally, that ought to be 0, so you can see that perhaps this is not a very good amplifier. You might think, well, we just have an r sub e down here in the denominator. Why don't we just make it as large as possible? Well, the problem with making r sub e larger is that you're going to start to reduce your emitter current. If you reduce your emitter current, then you're going to make r sub e larger. If you make r sub e larger, you're going to start lowering down your differential gain. Let's go ahead and calculate the differential gain. R sub E is 5 kilo ohms, and here we have 2 times 50 in the denominator. We get 50 here for the differential gain, but what I'd like you to notice is that little r sub E is in the denominators of both the common mode gain and the differential gain. So if you try to fiddle with big r sub E to lower down the common mode gain, you're just going to increase little r sub E and screw up your differential gain at the same time. So what we need is an independent way of changing big r sub E. We want to lower down the common mode gain without affecting our differential gain. What can we do? One way is to replace it with a current source. So let's just assume here that we've completely gotten rid of our emitter resistor and replaced it by a perfect 1 milliamp current source. What's going to happen? Let's label this voltage V sub E. Let's call this emitter current 1 and emitter current 2 over here. Let's apply the Kirchhoff voltage law across the emitter of first transistor. So we'll start with Vn1, and then we're going to have a voltage drop of IE1 times the emitter resistance that we have right here, and then we'll also have our 0.7 volt drop. We can apply the same equation across transistor 2, so we have an emitter voltage being input voltage 2 minus IE2 times R sub E minus 0.7 volts. I can also apply the Kirchhoff current law at node VE. So we have 2 emitter currents flowing into the node, and those should equal the I of our current source. If we assume that this DC current of 1 milliamp flows equally between the 2 resistors, then we ought to have 500 microamps flowing through both emitters. It means that our little R sub E is 26 divided by 0.5. In this case, it works out to about 52 ohms. What I'd now like to do is take these 2 equations and subtract them from one another. On the left side, we're going to wind up with a 0. On the right side, we're going to wind up with Vn1 minus Vn2. Then we're going to have IE1 minus IE2 times our emitter resistance, and then the 0.7 volts are subtracted out. This is just my differential voltage. Let's move VD to the left side of the equal sign, and let's divide by R sub E. I'm now going to rewrite this equation with the I on the left side, and I'm going to add these 2 equations to one another. So we wind up here on the right with 2 times my emitter current through transistor 2. Let's solve for that current. So it's just 1/2 times the expression on the left. Let's now solve for V out 2. We'll start at 10 volts and work our way down. So it's going to be VCC, which is 10 volts, and then we need to subtract the collector current flowing through this resistor times the collector resistance, which in this case is 5 kiloohms. We'll plug the numbers in a moment. So the collector current is beta over beta plus 1 times the emitter current. And I already have an expression for the emitter current down here. So I'm going to substitute this expression in. We can identify some constants in this expression. VCC is just a constant. I is also just a constant. So when we rewrite the expression, we wind up with a bunch of constants plus some number times V sub D. This number right here is just our differential gain. You'll notice that our output voltage depends only on the differential voltage. VCM doesn't appear in this expression at all. Therefore, the common mode gain for this circuit is 0. The differential gain for this circuit is nearly R sub C divided by 2 little r sub e, which is exactly the gain that we found at the beginning of this video when we used a very simple AC analysis on this circuit. If we plug in numbers for this particular example and treat this ratio as 1, then we have 5 kiloohms for R sub E and 52 ohms for little r sub e, and we wind up with a differential gain of about 48. So it's roughly what we had previously when we used an emitter resistor, but we've zeroed the common mode gain all the way down to 0. What we've shown here is that we have an interesting application for a current source. If we have some way to build a perfect current source, then we can use it to replace resistors in our circuits and lower down the common mode gain in the meantime. But how can you build current sources? Current sources would actually be really useful for this reason. But how can we start with, say, a bunch of transistors and voltage sources and create a current source? That's going to be the subject of our next video, current mirrors.